Come on, my dears, let us begin with a new chapter. Very interesting, very important from examination point of view, bit lengthy also. Let us begin with chapter number 6, Thermodynamics. Fine. In the beginning of this chapter, we are supposed to have good understanding regarding two words. One is heat energy, another is temperature. Okay? Let us try to understand these two words, and at the same time, let us try to have some points of distinction between heat energy and temperature. Okay? So let us see some points of differences between heat energy and temperature. Fine. For heat energy, I have written all the points over here, and for temperature, I have written over here. Okay? Fine. Now tell me, what is heat energy? It is the total of all internal kinetic energies associated with all the constituent particles of a given body. Total of all sorts of internal kinetic energies of all the constituent particles of a given body is called its heat energy. Correct? Tell me, which three types of motions can molecules of a body perform? Three types of motion: translational motion, then rotational motion, and vibrational motion. Correct? Pertaining to all these three types of internal motions, whatever is the kinetic energy of the whole body, that is known as its heat energy. Correct? Fine. Then tell me, what is temperature? Temperature gives us measure of average internal kinetic energy per one constituent particle of a given body. Why do we say it gives us measure of average internal kinetic energy per one constituent particle? Why we say like that? Because remember, if average internal kinetic energy per one molecule or per one constituent particle is more, then temperature is more. And if average kinetic energy per one constituent particle is less, then temperature is less. Correct? Remember, temperature itself is not energy. Temperature gives you measure of average internal kinetic energy per one molecule of a body. Correct? Because in second semester we had studied average kinetic energy, average of half mv square. Remembered? It was 3/2 kT, or in short, it is proportional to capital T. Correct? Greater is the kinetic energy per one molecule, greater is the temperature. Smaller is the kinetic energy per one molecule, smaller is the temperature. Correct? So temperature gives us measure of average internal kinetic energy per one molecule of a body. Got it? Fine. Second point of difference, heat energy is after all one form of energy. One form of energy. Correct? Fine. Out of different types of energy, out of different types of forms of energy, this is one form of energy. Heat energy is a form of energy. What is temperature after all? Let us try to give its introduction. It gives us measure of degree of coldness of a body or hotness of a given body. How much cold a given body is, how much hot a given body is. If you want to have measure of degree of hotness or coldness of a given body, then you need to define a physical quantity called temperature. Correct? That's what I have written here. It is a measure of degree of coldness or hotness of a body. Got it? Point number 3, it is a reason to have heat energy with a body is a reason, and because the body has heat energy, then we have temperature of that body. So temperature of a body is its post effect. Come on, heat energy is a reason and its post effect is temperature. Correct? So So temperature is an effect. Okay. What about unit of heat energy? You can measure heat energy in calorie or joule or erg. So there are three units: calorie, joule and erg. Here for measuring temperature, we will see in the later part of this chapter, there are three units: degree centigrade, degree Fahrenheit and Kelvin. Degree centigrade, degree Fahrenheit and Kelvin. Correct? These three are the units to measure temperature. Fine. Now let us see what is called thermodynamics. What is called thermodynamics? See, right from beginning, we have made our constant attempts to convert freely available heat energy, which is a natural source of energy, to convert it into mechanical energy because it is more useful. Once you get mechanical energy, then using electric dynamo, you can convert it into electrical energy. And using that electrical energy, you can run all the household appliances, you can run the machines of different industries, you can just use it for the purpose of human welfare. Correct? So the mankind is in constant making efforts for converting heat energy into mechanical energy. Fine. Then under which conditions and how much transformation can be made possible? For that transformation, what are the required devices? Correct? This everything is studied in one branch of physics, which is called thermodynamics. So how would you define it? A branch of physics in which we deal with conversion of heat energy into mechanical energy, and we try to study the necessary conditions and devices for such conversion is called thermodynamics. Correct? A branch of physics in which conversion of heat energy into mechanical energy is studied and also the necessary conditions and devices are studied is called thermodynamics. Correct? Fine. Now, let us explain two words. One is system, another is surrounding. What do you mean by system and what do you mean by surrounding? Very simple. See, in whichever part of the entire universe or in whichever object of the entire universe you are interested from thermodynamical study point of view, that part or that object is treated as, is taken as system, and the rest part of the universe, that rest part of the universe which directly affects our system is taken as its surrounding. So any part of universe, the thermodynamic study of which we have to make is known as system, and that rest part of the universe which directly affects our system is called surrounding of that system. Correct? So when you consider two parts of universe which affect each other, correct? Out of these two parts which interact, which undergo some exchange of energy, out of these two parts, you can take any one part as a system and the rest part you can take as a surrounding for that particular system. Which part should be taken as a system, which part should be taken as a surrounding, that is what we have to decide. We are quite free to decide that. Okay? Out of two parts, any one part can be taken as system. At that time, the rest part should be taken as a surrounding. Got it? Fine. So, a part or an object of universe whose thermodynamic study we have to make is called a thermodynamic system, and that rest part of the universe which directly affects our system is called surrounding of that system. Got it? Or you may define this way: out of two parts of universe which interact with each other, if one is taken as a system, then the rest should be taken as a surrounding for that system. Simple? Fine. System may be one-dimensional, maybe two-dimensional, or maybe three-dimensional. Thermodynamic system may be one-dimensional, maybe two-dimensional, maybe three-dimensional. Fine. It may comprise of one or more than one objects. It may consist of one or more than one objects, which are normally called components of a system. Components of a system. Simple. In a thermodynamic system, there may be some radiation. Radiation is a common name given to all sorts of electromagnetic waves. So, in a system, there may be only radiation also. That is also a system. Fine. What do you mean by wall of a system? The boundary which separates system and surrounding is called wall of the system. A boundary which separates system and surrounding is called its wall. Depending upon type of wall, we can have different types of interaction between system and surrounding. If the wall is non-conducting, we call it insulating wall. Then we may call it adiabatic wall, in which there is no heat exchange between system and surrounding. If the wall is conducting, which we call diathermic wall, conducting wall, then there may be some heat exchange between system and surrounding. So, depending upon different types of wall, there may be some different types of interaction between system and surrounding. Okay, fine. What do you mean by mechanical coordinates? Generally, in every branch of physics, the macroscopic description of a system is made by using those physical quantities which can be measured practically, such as position, velocity, acceleration, etc. Such physical quantities are called mechanical coordinates. Mechanical coordinates. Okay, fine. Then using mechanical coordinates, we can find out potential energy of a system, we can find out kinetic energy of a system, and then after, by adding these two energies, we may find out mechanical energy also. Got it? Fine. What do you mean by thermodynamic state variables? Thermodynamic state variables. See, when you consider a thermodynamic system, then there are some physical quantities which describe the state of that thermodynamic system, and depending upon type of interaction, one or more than one such physical quantities may change with time. Any physical quantity changing with time is called variable. But because variables like pressure, volume, temperature, internal energy, these are the variables which may change and then which describe the state of the thermodynamic system are called thermodynamic state variables. Thermodynamic state variables. I repeat, a physical quantity which changes with time is called variable. A physical quantity which describes the thermodynamic state of a thermodynamic system is called thermodynamic state variable. And they are, come on, pressure, volume, temperature, quantity of heat. These are the physical quantities which describe the state of a thermodynamic system. That's why we call them thermodynamic state variables. Thermodynamic state variables. Fine. Then we go for thermodynamic process. Whenever any given thermodynamic system interacts with the surrounding, at that time it simply undergoes some process in which it keeps on changing its thermodynamic state. Such an interaction in which the state is being changed is known as thermodynamic process. An interaction between system and surrounding whereby thermodynamic state of a thermodynamic system is getting changed is called thermodynamic process. Thermodynamic process, correct? Before and after the thermodynamic process, the system is said to be in that state in which all the thermodynamic state variables keep constant with time, then it is said to be in the equilibrium state. And when the process is going on at that time, one or more than thermodynamic state variables may change with time. So it is just passing through several intermediate thermodynamic states, and finally it will reach to the final equilibrium state. Correct? Fine. What do you mean by an isolated system? A system which does not interact with the surrounding in any way is called an isolated system. A system which does not interact with the surrounding at all is called an isolated system. For such system, because it does not interact, because it does not undergo any thermodynamic process, its all thermodynamic state variables keep constant with time. They do not change with time, they remain invariant with time. Okay, fine. Such a system is called an isolated system. Then, what is the difference between heat energy and heat? Normally in physics, we just use these two words as synonymous. No, they do not have same meaning. From physics point of view, meaning of heat energy and only heat, they are different. I am showing you. Whenever two bodies are bring in contact, in thermal contact with each other, having different temperatures, we practically find that heat energy is lost by the body which has higher temperature, and heat energy is absorbed by that body which is having lower temperature. Correct? And after this interaction is over, both the bodies have acquired equal temperatures. Correct? Fine. And when they have acquired equal temperatures, by that time, during that time, they have undergone some heat energy, some exchange of some heat energy. That amount of heat energy exchange between two bodies itself is known as heat. Amount of heat energy exchange between two bodies having different temperatures when they are brought in thermal contact with each other is called heat. Remember, heat energy can be possessed by a body, but heat cannot be possessed by a body, because it is that amount of energy which is involved in the interaction process. Correct? It cannot be acquired, it cannot be assumed, it cannot be possessed by a single body. Correct? I repeat, amount of heat energy exchange is called heat. Heat energy can be possessed by a body, but heat cannot be possessed by a body. Got it? Then what do you mean by mechanical energy and work? See, amount of mechanical energy exchange between system and surrounding is called work. Amount of mechanical energy exchange between system and surrounding is called work. Here also, mechanical energy can be possessed by a body, but work cannot be possessed by a body, because work is that mechanical energy which is getting exchanged in the thermodynamic process. It cannot be possessed by the either body. Correct? Fine. What do you mean by equation of state? An equation involving thermodynamic state variables which describes the thermodynamic state of a thermodynamic system is called an equation of state. For example, in second semester, you had studied one such equation of state for ideal gas. It was none but this: P into V equals to mu RT, where P is pressure, V is volume, mu is number of moles of molecules of a gas, R is universal gas constant, capital is absolute temperature of a gas. Okay? An equation in which there are thermodynamic state variables and which describes the thermodynamic state of a system is called an equation of state for that thermodynamic system. Okay, fine. Now there are two types of state variables. There are two types of state variables. One is called extensive state variables. Another type is called intensive state variables. Let us see one by one. First of all, extensive state variables. the state variable which is different for whole system and some part of it is called an extensive state variable. For example, mass of the entire system is more and mass of its part is less. Volume of entire system is more, volume of some part of that system would be less. Internal energy of entire system would be more, internal energy for some part of that system would be less. I mean to say, a state variable which is different for entire system and for some part of it is called an extensive state variable. On the other side, let us see now intensive state variables. A state variable which is same for the entire system and for some part of it is called an intensive state variable. For example, density, pressure, temperature. Whether you find out density of the entire system, say it is a gas system, whether you find out density of gas in the entire system or you find out density of gas in some part of the system, it would come out same. Whether you find out pressure of entire gas system or pressure of some part of that gas system would come out same. Whether you measure temperature in the entire system or you measure temperature in some part of the system, that would come out same. So such physical quantities, not only they are state variables, but they are such state variables which are same for the entire system and for some part of it, which are called intensive state variables. Correct? Come on, repeat both the definitions. The state variables which are different for a given entire system and some part of it are called extensive state variables, and the state variables which are same for given entire system and for some part of it are called intensive state variables. Correct? Point. What do you mean by thermal equilibrium? When system is said to be in thermal equilibrium with the surrounding, very simple. Whenever there is no heat exchange between system and surrounding, we say there is no thermal interaction between them. At that time, system and surrounding are in thermal equilibrium with each other. When there is no exchange of heat energy between system and surrounding, they are said to be in thermal equilibrium with each other, or they are said to be in mutual thermal equilibrium. Got it? Fine. Then what do you mean by mechanical equilibrium? When there is no exchange of mechanical energy between system and surrounding, then that system and surrounding are said to be under mechanical equilibrium. Correct? No mechanical interaction, then mechanical equilibrium. No thermal interaction, then thermal equilibrium. Simple? Fine. What do you mean by chemical equilibrium? When there is no motion of any chemical component between system and surrounding, then we say there is a chemical equilibrium established between system and surrounding. When there is no motion of any chemical component between system and surrounding, we say the type of equilibrium between them is said to be chemical equilibrium. Correct? No thermal interaction, then thermal equilibrium. No mechanical interaction, then mechanical equilibrium. No chemical interaction, then chemical equilibrium. When a system is said to be under thermodynamic equilibrium, very simple. Whenever any thermodynamic system has all these three types of equilibriums at a time, it is said to be in thermodynamic equilibrium state. A system which is under thermal equilibrium also, mechanical equilibrium also, and chemical equilibrium also is said to be in thermodynamic equilibrium. Got it? Fine. Now let us study one very important result, 0th law of thermodynamics. This result is very important and we just call it 0th law of thermodynamics, which is very basic, very fundamental, very important. Look, here I have drawn these two figures in which you must consider all these walls which are shown with slanting lines with this sort of shade. You must take them as non-conducting wall. And if I am not showing you any shade, then this plain wall you should take it as a conducting wall. Non-conducting wall is shown with a shade with the slanting lines, and without slanting lines, that is conducting wall. Non-conducting wall is also called insulating wall. Insulating wall. Sometimes we call it adiabatic wall. And this is the conducting wall, which sometimes we call diathermic wall. Diathermic wall. Okay, fine. Now you can see in the figure, there are three thermodynamic systems which are shown in the figure, A, B and C. Tell me, how to find wall between A and B? It is conducting. How to find this wall between B and C? It is also conducting, correct? So there can be some heat energy exchange between A and C. There can be some heat energy exchange between B and C also. But because the wall between A and B is non-conducting wall, there cannot be any exchange of heat energy between A and B right now. Because this wall is adiabatic wall, insulating wall, will not allow any exchange of heat energy between A and B, correct? So at present, you can say there is some thermal interaction between A and C, between B and C. But at present, there is no thermal interaction between A and B. Fine. Tell me, how long this heat exchange will continue between A and C and between B and C till their temperatures become equal. After some time, temperatures of these two bodies have become equal. That's what I have written here. TA equals to TC, and come on, temperatures of B and C also have become equal. Then you may write TB equals to TC. Fine. Now tell me, right hand sides are same, so left hand side also must be same. So TA must be equal to TB. TA must be equal to TB, correct? Then if temperatures of A and B have become same, meaning thereby there should not be any thermal interaction between A and B, correct? But how to check that fact, we want to check whether there is some thermal interaction between A and B or not. For that what you should do? You should remove this non-conducting wall and you should replace it by this conducting wall, correct? You should provide enough opportunity to these two systems so that they may interact, correct? But practically what do we find? When we replace these conducting and non-conducting walls, when we interchange them, here you can see now there is non-conducting wall and here there is conducting wall, correct? After that, practically we find that though we are providing conducting wall between A and B, then also there is no heat exchange between A and B. And because there is no heat exchange, you can say they also have acquired thermal equilibrium mutually. Fine. Earlier what was the condition? A had acquired thermal equilibrium with C, B also had acquired thermal equilibrium with C, and now tell me, here what do you notice? A and B also have acquired thermal equilibrium with each other. So the same result, when you just state it in a sentence, that will give you the statement for 0th law of thermodynamics. Very simple. When two thermodynamic systems A and B are in thermal equilibrium with a third system C, then those two systems A and B are also said to be in thermal equilibrium with each other. This very statement is called 0th law of thermodynamics. I repeat, when two systems A and B have thermal equilibrium with third system C, then those two systems A and B also are said to be in thermal equilibrium with each other. Full stop. This very statement is called 0th law of thermodynamics, correct? But tell me, how we are sure that these two are in thermal equilibrium? So just to check that condition of equilibrium between A and B, what we have done? We have practically measured their temperatures, and then after when we come to know that temperatures are equal, then we are sure that yes, there is some thermal equilibrium between A and B. So I mean to say, this zeroth law of thermodynamics we could give on the basis of thermal equilibrium. But how could we check that thermal equilibrium state between A and B? Using a physical quantity called temperature. So remember, there is a physical quantity named temperature, which is very important, which exists, and that is why we could check the equilibrium condition between A and B. So what is the conclusion of this discussion of zeroth law of thermodynamics? Conclusion is that there exists an important physical quantity called temperature in thermodynamics, using which we can check the equilibrium condition between two given bodies. Got it? Fine. What do you mean by phase diagram of a substance? Phase of a matter. Phase means form. There are three forms of a matter. There are three main states of a matter. There are three main phases of a matter: solid, liquid and gas. Correct? But out of these three phases, in which phase a given matter or given substance would exist, that depends on two factors: pressure and temperature. Pressure and temperature. For different combinations of pressure and temperature, given substance is found to be existing in different phases. So the two factors which decide the phase of a substance are pressure and temperature. Then what we do in laboratory? In laboratory, we keep a given substance at different pressure, different temperature, and then we just note down practically in laboratory the corresponding state of that substance, and we just prepare a table of observations in which we note down at this pressure, this temperature, this is the state of the body, this pressure, this temperature, this is the state of the body, like that. And then from that observation table, we plot one graph of pressure versus temperature. That very graph which is used to find out the phase of a substance itself is known as phase diagram. What is it called? Phase diagram. Yes, that phase diagram is a graph of pressure versus temperature. I had drawn that graph over here, but before we go for understanding that phase diagram, there are some elementary facts which you must understand and remember, because they will be utilized in the further discussion. Not given nicely in the textbook, I am just describing you here. Look, process of conversion of solid state into liquid state is called fusion process. Process of conversion of solid into liquid is called fusion. Speak reverse. Process of conversion of liquid into solid is called condensation. What is it called? Condensation. Fine. Process of conversion of liquid into gas is called vaporization. Speak reverse. Process of conversion of gas into liquid is called liquefaction. Liquefaction. Okay, fine. Process of conversion of gas into solid is called solidification, and process of conversion of solid into gas is called sublimation. Is called sublimation. Example for sublimation: the camphor. Camphor is a substance which sublime, which is an example of sublimation process. It directly transforms from solid to gaseous state. Okay. Another example of sublimation process is dry ice, which is solid form of carbon dioxide gas. Correct. It is also an example of sublimation. Fine. Please remember this triangle for mutual conversions. Okay. Now, I have drawn one more figure to explain you one fact. When two phases, two states of a matter are said to be in equilibrium with each other. When? I am showing you. Consider a flask in which some liquid is filled, okay, which is enclosed from the top with the help of some lid or some cover. And now tell me, at room temperature, there are certain molecules in this liquid which have higher kinetic energies, and they may leave this liquid surface while moving randomly. And if they leave this liquid surface, that process is known as vaporization. What is it called? Vaporization. Fine. Then after, what happens? then once the vapor is collected over here, they are in the gaseous state, and the molecules of this vapor, they just perform random motion, and when they perform random motion, some of them may re-enter into the liquid. That process is called liquefaction. Process of conversion of gas into liquid is called liquefaction, correct? So here what will happen? The liquid is getting transformed into vapor, and some of the molecules, they re-enter into the liquid. That process is nothing but liquefaction. Suppose the pressure and temperature of this vapor are such that the rate of vaporization and rate of liquefaction are same, then we say that this substance exists in liquid state also and exists in gaseous state also. At that time, liquid and gaseous state are said to be in equilibrium with each other. I mean to say, in general, whenever any two states of a substance are in equilibrium with each other, in that process what will happen? The number of molecules going from one state to another state and number of molecules coming back from second state to first state are equal on average in equal interval of time, correct? Then we say that substance coexists keeping equilibrium in both the states, correct? So whenever any substance coexists in two states keeping equilibrium between them, then number of molecules getting transferred from one state to another state and getting transferred from another state to first state are equal on average in equal interval of time. Then we say substance coexists in both the states keeping equilibrium with each other. Got it? Fine. Now look at this diagram. This is pressure versus temperature diagram. For a given substance, the typical phase diagram is this. Here I have written this region as a solid region, this particular region as a liquid region, and this region is gaseous region. Then you may have a question, why this region is called solid region? The reason is that if you take any point in this region and if you find out corresponding pressure and temperature, and if you keep given substance at that pressure and that temperature in laboratory, then we find practically that substance exists in solid state. Because it exists in solid state, we call this entire region as solid region. Fine. This region is called liquid region because for the pressures and temperatures at any point chosen in this region, the substance is found to be existing in liquid state in laboratory. That's why we call this region as liquid region. Similarly, this region is called gaseous region. Fine. Now there are three curves I have shown in the diagram: curve OA, curve AB, and curve AC. Process of conversion of solid into liquid is called fusion process. That's why this curve AB is called fusion curve. Process of conversion of liquid into gas is called vaporization process. That's why this curve AC is called vaporization curve. Correct? Then the process of conversion of gas into solid is called, process of conversion of solid into gas. Solid into gas is called, sublimation. Process of conversion of solid into gaseous state is called sublimation. That's why this curve is called sublimation curve. Okay. So there are three curves. Sublimation curve OA, fusion curve AB, and vaporization curve AC. Got it? Fine. Now, if you select points on this fusion curve, then those points are said to be present in both the regions, solid also and liquid also, because members of intersection set are said to be present in both the sets. If you take points exactly on this fusion curve, they are present in these two regions at a time. Correct? What is the physical meaning of that sentence? See the meaning from physics point of view. For the pressures and temperatures corresponding to all these points on this fusion curve, the substance is found to be coexisting in solid and liquid simultaneously in equilibrium. Fine. Similarly, for the points chosen on this vaporization curve, for the corresponding pressures and temperatures, the substance coexists in liquid and gaseous state keeping equilibrium with each other. Then, for the pressures and temperatures corresponding to the points chosen on the sublimation curve, substance is found to be coexisting in equilibrium in solid and gaseous state. Fine. But now if you select this very point, which point? Point A. Where do you find it? It is present in all the three regions, solid also, liquid also, gaseous also. Because it exists in all the three regions in the phase diagram, we have to say for the corresponding pressure and temperature, substance must be coexisting in equilibrium in all the three states, solid, liquid and gaseous. Because substance is coexisting in all the three states of a matter, we call that very point as triple point. What do we call it? Triple point. How would you define triple point? Very simple. A point obtained in the phase diagram of a given substance for the corresponding pressure and temperature at which all the three states of that substance coexist keeping equilibrium with each other is called triple point of that substance. I repeat. A point obtained in the phase diagram of a given substance, comma, for the corresponding pressure and temperature at which all the three states of that substance coexist keeping equilibrium is called triple point of that substance. Last time. A point obtained in the phase diagram of a given substance, comma, for the corresponding pressure and temperature at which all the three states of that substance coexist keeping equilibrium is called triple point of that substance. Got it? For different substances, we get this triple point for different combinations of pressure and temperature. Correct? So this position of this triple point may change depending upon type of substance. Got it? Fine. If you plot such phase diagram for H2O, then you will have one triple point there also, and at that very point, what is the corresponding pressure, what is corresponding temperature, we are supposed to remember those two values because they are given in the textbook. Simple. At the triple point of H2O, the temperature is 273.16 Kelvin. 273.16, that many Kelvin. But what is the pressure at the triple point of H2O? Remember, it is equivalent to, this is the sign of equivalence. When I am putting three line segments, it is sign of equivalence. This pressure is equivalent to 4.58 millimeter high column of mercury. Hg means mercury. Whenever pressure is expressed in terms of certain height of column of certain liquid, you must understand that pressure is nothing but hydrostatic pressure, which should be given by the formula rho GH. You know rho GH. Come on, rho is density, G is acceleration due to gravity, H is height of given liquid column. Correct? Use the same formula. PA equals to, I am finding that pressure at the triple point of H2O by this formula rho GH. But rho is the density of given liquid. Given liquid is right now mercury, for which density is well known, 13.6 gram per centimeter cube. What about CGS value of G? 980 centimeter per second square. What about height? It is 4.58 millimeter converted into centimeter. Multiply by 10 raised to -1. Correct? Fine. Now simplify. Answer is 6104.224. This many dyne per centimeter square. This many dyne per centimeter square. Okay? You want to convert it into Newton upon meter square, that is Pascal. You should multiply this value by 10 raised to -1. Then it will become 610.4. That many Newton upon meter square. Got it? Fine. Now, we begin another topic, that is thermometry. What do you mean by thermometry? A branch of physics in which we deal with measurement of temperature is called thermometry. In this branch, we develop new methods for measurement of temperature. We just prepare new devices for the measurement of temperature. Such a branch is called thermometry. Fine. Now, what do you mean by thermal sensitive substance? Thermally sensitive substance is that substance which has some property which depends on temperature. Correct? So, if temperature will change, that property will change. Such a substance whose some property is getting changed with the change of temperature is called thermally sensitive. thermally sensitive. What do you mean by thermal property? A property of a given body which changes with the change of temperature is called thermal property, correct? When the property of a body gets changed with the change in temperature, that body is said to be thermally sensitive and that property is said to be thermal property. Simple. I can give you 4 examples for that thermal property. Suppose length of a metallic wire. In 3rd semester you will study about electrical resistance also, and then just consider that example also, electrical resistance of a metallic wire. Then volume of a gas at constant pressure, and then pressure of a gas at constant volume. I repeat all the 4 examples. Length of metallic wire increases when temperature increases, means it is a thermal property because it changes with temperature. Then electrical resistance of metallic wire is also a thermal property. It is also increasing with the increase of temperature for metallic wire. Then volume of a gas at constant pressure, and then pressure of a gas at constant volume. Remembered from Boyle's law, V varies as T, V varies as T. So as temperature will change, volume will change, correct? So volume is also a thermal property. Then remember Gay-Lussac's law, P varies as T. So when temperature will change, pressure will change. So pressure is also a thermal property. Okay. So remember, such examples are those physical quantities which change with the change in temperature. They are all thermal properties. Okay. Come on, my dears. Let us see what is called temperature function. Fine. From the study of 0th law of thermodynamics, we had concluded that there exists some important physical quantity called temperature, using which we can have the checking of thermal equilibrium between 2 given bodies, correct? Fine. Now, if 2 given bodies are under thermal equilibrium with each other, then they both have same temperature, correct? But now we want to measure that temperature. Fine. Then for that we need to have some property of a body which should change with temperature, which we call thermal property. But among all the thermal properties just now I told, the most reliable thermal property is the pressure of a gas at constant volume. By measuring pressure of a gas at constant volume at different temperatures, we can have measurement of temperature very accurately. And now for that we have decided to take that property as most reliable property. Fine. Which one? Pressure of a gas at constant volume. Okay, fine. Now tell me, a function with the help of which we can express temperature of a body lying in a definite thermal equilibrium condition by a definite real number is called temperature function. A function with the help of which we can express temperature of a given body lying under definite thermal equilibrium by a definite real number is called temperature function. For example, when you take pressure of a gas at constant volume, as a most reliable thermal property, then when the pressure will change, then temperature will change directly proportional. Why? You know, at constant volume, which law will be obeyed? Gay-Lussac's law. And what is that Gay-Lussac law? P varies as T. Now speak reverse. T varies as P, correct? So mathematics will say when pressure will change, temperature will change. So temperature is said to be function of pressure. That's why I am putting P in bracket. So temperature is taken right now as a function of pressure, which is directly proportional to pressure. Okay, fine. Such a function is called temperature function. Fine. What do you mean by thermometer? A device with the help of which temperature of a given body lying under definite thermal equilibrium condition can be measured by a definite real number is called thermometer. I repeat, a device with the help of which we can measure temperature of a given body lying in a definite thermal equilibrium condition by a definite real number is called thermometer. Last time, a device with the help of which we can measure temperature of a given body lying under definite thermal equilibrium condition by a definite real number is called thermometer. Fine. Come on, now let us see about constant volume gas thermometer. Here is ideal gas thermometer in which the pressure of a gas at constant volume is taken as most reliable thermal property. The construction of this thermometer is not there in your syllabus. Let me give you some brief idea. We just take some globe of glass, you can say spherical shell of glass or a bulb of glass, in which we fill in some gas with very low density. And then after, when we keep that gas at different pressures, then its temperature is different. And then when we change the temperature, the pressure is also getting changed. That pressure we can measure practically. And then after, we can just plot a graph of pressure versus temperature. And when that graph is plotted, it is found to be like this. Correct? Fine. Now, if you extend this graph backward, it meets with this temperature axis at this very point, where temperature is found to be in degrees centigrade. It is found to be minus 273.15 degrees centigrade. Fine. Now, let us take different gases in the same bulb of glass. Let us take different gases, okay? Say gas A, gas B, gas C, like that, okay? And then after, when we plot this graph again of pressure versus temperature, we get graphs like this, correct? Have you noticed one thing? When all these graphs are extended backward, they meet at the same point where the temperature is still the same. It is minus 273.15 degrees centigrade, correct? Now, this must be the lowest temperature because this is the temperature for which pressure has become 0, correct? When pressure is becoming 0, the temperature must be lowest. And that lowest temperature, if you try to measure using gas A or using gas B or using gas C, every time it comes out to be same. Meaning thereby, such a measurement of this temperature does not depend on type of gas. So, it is an absolute temperature. Because it does not depend on type of gas, we call such temperature as, which is independent of type of gas, we call it absolute temperature. What do we call it? Absolute temperature. The temperature whose measurement does not depend on type of gas is called an absolute temperature. And to measure absolute temperature, we have selected another SI unit, which is Kelvin, okay? So, now, if you measure this temperature in Kelvin, because it is the lowest temperature, then we should take it as 0 Kelvin. And then that 0 Kelvin is called, no doubt it is absolute temperature, because value wise it is 0, we call it absolute zero temperature, okay? So, the same temperature in degrees centigrade we take in Kelvin as 0 Kelvin, okay? Fine. Now, before we go for this temperature scales, one is in Kelvin, another in degree centigrade, another in degree Fahrenheit. Let me show you two formula relating these different temperature units. Very simple. Look, mutual conversion relations. If you take temperature in degree centigrade by symbol Tc, and if you add 273.15, then you will get the temperature value in Kelvin. So, you can write this many Kelvin, correct? If you got temperature value in degree centigrade, if you just show it by symbol Tc, multiply by 9, divide by 5 and then add 32, then you will get the temperature value in degree Fahrenheit. Got it? Fine. Now tell me, let us start with the temperature scale in Kelvin. This is the Kelvin scale, this is degree centigrade scale, and this is degree Fahrenheit scale. What was the lowest temperature in Kelvin? It was 0 Kelvin, okay? Let it be here, okay? 0 Kelvin, fine. Now, just put here 0 Kelvin. Put here 0. find out Tc, it will be minus 273.15 degrees centigrade. Here it is, minus 273.15 degrees centigrade, correct? And the same value of temperature in degree centigrade, you may put it here. Simplify, you will get temperature value in degree Fahrenheit equal to minus 459.69, that many degree Fahrenheit. Okay, fine. Now, for preparing this temperature scale, we just select two fixed points, and one of those two fixed points is melting point of ice at 1 atmospheric pressure, which is also called ice point, and that ice point is nothing but 0 degrees centigrade. It is a well known temperature to everybody, correct? You must have remembered. And now you put that 0 degree centigrade value here. 0 plus this will give you 273.15 Kelvin. That should have written here 273.15 Kelvin. Got it? Put here 0 degree centigrade, then temperature in degree Fahrenheit you will get 32 degree Fahrenheit. Here it is 32 degree Fahrenheit. Got it? And then another fixed point is nothing but boiling point of water at 1 atmospheric pressure, which is also called steam point. And you must remember that temperature also 100 degrees centigrade. Got it? Put here 100. 100 plus this will give you 373.15 Kelvin. Here it is 373.15 Kelvin. Got it? Put here 100 degree centigrade value and simplify, you will get temperature in degree Fahrenheit equal to 212 degree Fahrenheit. Okay? So this is the Kelvin scale, this is degree centigrade scale, and this is degree Fahrenheit scale. Okay? Fine. Now, what is the temperature of healthy human body? Temperature of healthy human body is 37 degrees centigrade. 37 degrees centigrade. Put it here, 37. Simplify, you will get the temperature, corresponding temperature in degree Fahrenheit equal to 98.6 degree Fahrenheit. Here it is 98.6 degree Fahrenheit. Okay. Please remember all these values. Okay. Fine. Now there is a special note you must understand and remember. 10 degree centigrade temperature is not equal to 10 degree Fahrenheit temperature. Temperature measured in degree centigrade equal to 10 degree centigrade is not equal to 10 degree Fahrenheit temperature. Okay? Because once you write the value here 10, then the degree Fahrenheit value that will not come out equal to 10. It will come out different value. Okay? So 10 degree centigrade temperature is not equal to 10 degree Fahrenheit temperature. Got it? But 10 centigrade degree is equal to 10 Fahrenheit degree. Now you may wonder why it is like that. See, this 10, it is not temperature, it is temperature difference measured in centigrade, correct? Similarly, this is also temperature difference measured in Fahrenheit. But when you want to show temperature difference, then you must write degree sign after C and after F, okay? If you write degree sign before C and before F, it shows you temperature. But when you write this degree symbol after C and after F, it does not show you temperature, it shows you temperature difference. So temperature difference of 10 centigrade degree is equal to temperature difference of 10 Fahrenheit degree. Okay? I repeat for the last time. If you write degree first and then if you are putting C or F, it gives you only temperature. If you are putting C or F first and then after you are putting degree symbol, it shows you temperature difference. And in one of the MCQ in this chapter, we will see that what is that temperature value which when measured in degree centigrade and measured in degree Fahrenheit comes out to be same mathematically. It is none but minus 40 degree centigrade temperature is exactly equal to minus 40 degree Fahrenheit temperature. You may put it here minus 40, then temperature in degree Fahrenheit also you get minus 40 degree Fahrenheit. So this is that numerical value which is same, and whether you measure it in degree centigrade or you measure in degree Fahrenheit comes out to be same. But it is true only for this particular value, not for other values. Okay? And when you place minus 40 degree centigrade here, correct? Minus 40 here, and if you find out this temperature in Kelvin, it comes out to be 233.15 Kelvin. Okay? Now let us go for what is called thermal expansion, what is called thermal contraction. Very simple. If you take any solid body if you increase its temperature, you know what happens? Come on, its length would increase, its surface area would increase, its volume would increase. And you can say when volume is increasing, it is nothing but expansion process, correct? So phenomenon of increase in volume of a solid body with the increase in its temperature is known as thermal expansion. Now speak reverse. If you decrease the temperature of a solid body, then length will decrease, surface area will decrease, volume will decrease, meaning thereby body is said to be getting contracted. That's why this phenomenon is called thermal contraction. Phenomenon of decrease in volume of a solid body with the decrease in its temperature is called thermal contraction. Okay, fine. Now here, just to explain this phenomena, we assume some representing model. And what is that model which represents the behavior of a solid body? It is this model in which the constituent particles are assumed to be joined with some elastic springs. You know why? Tell me. At room temperature, what all these constituent particles do? They perform thermal vibrations with some frequency and with some amplitude, correct? Fine. But when you increase its temperature, what happens? The kinetic energy of oscillation goes on increasing, and because of that frequency and amplitude both increase. So at that time, they just oscillate more with a bigger amplitude with greater frequency. So actually they are not joined by the springs, but then also they go on exerting intermolecular forces on each other as if they are bound by such elastic springs. So actually these springs are not there. We have just shown it in the figure. They are imaginary springs, but this model explains very well how the molecules or constituent particles oscillate with a greater amplitude and greater frequency with the increase in temperature. With the decrease in temperature, they will start oscillating with lesser amplitude, lesser frequency, correct? So this is the model which represents the behavior of a solid body during the change in temperature, okay? Similarly, you can think of this triatomic molecule also joined with the springs, okay? These springs are, once again I am reminding you, they are imaginary, okay? Fine. Now, you take a system of two constituent particles, two constituent oscillating particles of a solid body, and a potential energy made up of two molecules separated by distance r. I am just showing mathematically by this symbol u as a function of r. And then versus I am just plotting interatomic distance, okay? You can say interatomic potential energy versus interatomic distance, okay? Now tell me, when you plot this interatomic potential energy versus interatomic distance, that graph is found to be like this. Fine. Now tell me, see in the graph I have shown R0. You know what is R0? Average intermolecular equilibrium distance. Average intermolecular equilibrium distance. Now just consider this line which is passing through this R0, okay? Now tell me, how to find these two parts of this graph? This part on the left side, this part on the right side. They are not symmetrical about this vertical line. No, they are not symmetrical. And because they are not symmetrical, you can say graph is asymmetric. Graph is asymmetric. Asymmetric means non-symmetric. Graph is non-symmetric. And because of this non-symmetry of this graph, we find that when you increase the temperature, the thermal expansion of a solid body takes place. How does it take place? I am showing you. Consider this value of intermolecular potential energy, correct? Fine. At temperature T. And for this value, come on, you can just draw a horizontal line, correct? And then when that line is cutting this graph at these 2 points, you can just find out corresponding distance between two molecules. Here this is R minimum suppose, and this is R maximum. And then you find out average of these two distances. How would you find out average? Summation divided by 2. R minimum plus R maximum divided by 2. Let it be R0, which is here, correct, right now. Now you increase the temperature. When you increase the temperature, intermolecular potential energy increases. So U as a function of T dash I am writing, where T dash is greater than T, okay. At higher temperature, potential energy is higher, so I am just showing their value on upper side. Now corresponding to this value, you just draw horizontal line. It will intersect this graph at these 2 points. Now again you find out minimum value for R and maximum value for R. Let it be R minimum dash and R maximum dash. Again you find out their average. Again summation divided by 2 will give you R0 dash, and that R0 dash is between these two and it is here, correct. Have you noticed one thing in the figure? This average intermolecular equilibrium distance R0 dash is greater than this because it is on right hand side. This value is greater than this, that's what I am writing here. R0 dash is greater than R0. So what does it mean? Average intermolecular equilibrium distance would increase if you increase the temperature. And if average intermolecular distance increases, suppose initially it is 10 units, and later on with the increase in temperature it becomes 15. So from 10 it becomes 15. What does it mean? That length of the body is increasing. When you increase the temperature of a solid body and if length is increasing, it gives you thermal expansion from linear point of view. That's why we call it linear expansion. What do we call it? Linear expansion. So linear expansion is due to non-symmetry of this graph, or you can say asymmetric graph between potential energy and distance is responsible for having linear expansion in a solid body, okay. If this graph would have been symmetric, suppose, if this graph would have been symmetric, then for any value of potential energy, you will get average intermolecular equilibrium distance same. And if that average intermolecular distance remains same, meaning thereby, though you are increasing the temperature, then length will not increase. But right now, practically we find that when temperature is increasing, length is definitely increasing. It is because of the fact of this asymmetry of this graph, and because of that what happens, as you increase the temperature, average intermolecular equilibrium distance goes on increasing. That's why this point is shifting on right hand side, which shows linear expansion. Got it? Fine. Now let us derive one formula for linear expansion. If you increase the temperature of a given solid body within small range, then practically we find that increase in length of that solid body is directly proportional to its original length. At the same time, it is also proportional to increase in temperature. When the same physical quantity depends on these two simultaneously, then you may write as a combined dependence this way: delta L proportional to L into delta T, correct? When this is proportional to this into this, remove this sign of proportionality, put some proportionality constant, say alpha. Now this proportionality constant alpha, in physics we have given specific name to it. It is called coefficient of linear expansion. Come on, coefficient of linear expansion, correct? Fine. Sometimes we call it linear expansivity, fine. Let us try to define alpha. Come on, make it subject of the equation. It will be delta L upon L upon delta T, delta L upon L upon delta T. Now just to give the definition of alpha, we normally what we do, we make the denominator 1 unit. So if delta T is taken 1 degree centigrade, put it here, then alpha will be delta L upon L, delta L upon L. Change in any physical quantity divided by its original value will give you fractional change in that physical quantity, correct? If this is increase in temperature, this will give you fractional or partial increase in the length, and the same partial increase in the length itself is known as alpha, that is coefficient of linear expansion. How would you define it? The partial or fractional increase in the length of a given solid body per 1 degree centigrade rise in its temperature is called coefficient of linear expansion for that solid body. I repeat, the fractional increase in the length of a given solid body per 1 degree centigrade rise in its temperature is called coefficient of linear expansion for that solid body, shown by symbol alpha. Come on, what about unit of alpha? length upon length, so it will have no unit. Come on, so unit of alpha will be 1 upon unit of temperature. If you take unit of temperature, say degree centigrade, it will be 1 upon degree centigrade, that is degree centigrade inverse. If you take unit of temperature as Kelvin, then 1 upon Kelvin, that is Kelvin inverse. Got it? Fine. Now, what about dependence? Alpha depends on what? Dependence of alpha is found to be practically on two factors. One is type of material of solid body and its initial temperature. From which initial temperature you are increasing temperature by 1 degree centigrade, depending upon the value of that initial temperature, value of alpha is varying. Okay? So, value of alpha depends on two factors, type of material of a solid body, and it also depends on initial temperature of a solid body from which you are increasing the temperature by 1 degree centigrade. Okay? Then, for linear expansion, just now we have obtained this formula, delta L equals to alpha L delta T, correct? For surface expansion, similarly, instead of increase in length, you may write increase in area, that is delta A. Instead of alpha, you may put beta. What is beta? Coefficient of surface expansion. Coefficient of surface expansion or surface expansivity. Fine. And instead of original length, you should write original area. Come on, delta T as it is, correct? Then for volume expansion, come on, instead of delta L, you may write delta V, correct? This is increase in volume if you are increasing the temperature. Then instead of alpha, you may put here gamma, which is called, gamma is called, come on, coefficient of volume expansion. What was alpha? Coefficient of linear expansion. Beta is called coefficient of surface expansion. Gamma is called coefficient of volume expansion. Here initial length, here initial area, here initial volume. Delta T is everywhere. Got it? Fine. Now from here, from this equation number 2, if you make subject of the equation say beta, it will be delta A upon delta T. Delta A upon delta T, correct? Come on, define the value of beta, I mean give its definition. The way we give the definition of alpha, you are supposed to give definition of beta. Very simple. The partial or fractional increase in the surface area of a given solid body per 1 degree centigrade rise in its temperature is called coefficient of surface expansion for that solid body. Similarly, what about definition of gamma? Definition of coefficient of volume expansion. Very simple. The fractional or partial increase in the volume of a given solid body per 1 degree centigrade rise in its temperature is called coefficient of volume expansion for that solid body, correct? Whether it is coefficient of linear expansion or coefficient of surface expansion or coefficient of volume expansion, all of them have same unit, which is degree centigrade inverse or Kelvin inverse. Got it? Fine. Let us see about photographic magnification. There are some solid bodies for which it so happens when you increase the temperature, whatever is the percentage increase in its original length, same is the percentage increase in its original width, same is the percentage increase in its thickness also. So, length, breadth and height or thickness, they undergo percentage wise same increase with the increase in temperature. And if it happens so, then the shape of the solid body remains same, only the size increases. And when size increases with retaining same shape, then we say as if it is photographically enlarged. Such a phenomenon is called photographic magnification. Photographic magnification. For example, you take this metallic plate having this hole at this position. Now, if you increase the temperature and suppose this length increases by say 50%, suppose, then this breadth also will increase by 50%, correct? The diameter of this hole also will increase by 50%, like that. So, after that magnification, the shape of the body will appear like this. Now, tell me, shape is same, there is no change in the shape, okay? But there is a change in the size, there is increment in the size, correct? Then such bodies which undergo same percentage increase in linear expansion, same percentage you have surface expansion, same percentage you have volume expansion, such bodies are said to be enlarged photographically, and such bodies are called isotropic solid bodies. What are they called? Isotropic solid bodies. The solid bodies which undergo same percentage of linear expansion, same percentage of surface expansion, same percentage of volume expansion is said to be, such bodies are said to be isotropic bodies. They are always photographically enlarged, correct? If some of the photograph of you, if you like it very much, then what you do normally, you just go to the studio, you make it enlarge, and that is nothing but photographic enlargement. Same way this is also called photographic enlargement or photographic magnification, and such solid bodies are called isotropic solid bodies. Okay, fine. Let us go for anomalous expansion and contraction of water. Anomalous expansion and contraction of water. See, normally for every substance, it so happens when you increase the temperature, then volume increases, and if volume increases, then density will decrease. But this is not true for increase of temperature of water from 0 to 4 degrees centigrade. For water, it so happens when you increase its temperature from 0 to 4 degrees centigrade, instead of volume increasing, volume goes on decreasing. And exactly at 4 degrees centigrade temperature, volume becomes minimum. When volume becomes minimum, naturally density would become maximum. At which temperature? 4 degrees centigrade. Such a abnormal behavior of water is called anomalous expansion of water. Anomalous expansion of water. Got it? What do you mean by anomalous contraction of water? I am showing you. Normally what happens when you decrease the temperature of any body, then when temperature is decreased, then volume will decrease. When volume will decrease, then density will increase. But this is not true for decrease of temperature of water from 4 to 0 degrees centigrade. When you decrease temperature of water from 4 to 0 degrees centigrade, instead of volume decreasing, volume goes on increasing. At 0 degrees centigrade, volume becomes maximum. When volume becomes maximum, the density would become minimum, correct? Then this is nothing but anomalous contraction of water. Anomalous contraction of water. Let me show you both the things in the graph now. Here is a graph of volume versus temperature. Here is a graph of density versus temperature for water. See in this graph, when temperature is increased from 0 to 4 degrees centigrade, correct? When you go this way, volume decreases, and here it becomes minimum. I am writing here V minimum. When volume has become minimum, natural density should become maximum. Here it is. At 4 degrees centigrade temperature, you can see density is at the peak, it is maximum, rho maximum, correct? Now talk about anomalous contraction. When you decrease the temperature of water from 4 to 0 degrees centigrade, look here, what happens? Volume goes on increasing. Here it becomes maximum. When volume is maximum, density should be minimum. Here it is. When you decrease the temperature from 4 to 0, density goes on decreasing. Here density becomes minimum. Got it? So these both the phenomena are shown in the graphs. One is the graph of volume versus temperature, another is the graph of density versus temperature. Simple. Now this anomalous expansion of water is a blessing for all the aquatic life. Aquatic or marine life, they reside in water, correct? Consider this water in a lake, okay? Now above the water surface we have atmospheric air, and suppose in winter season, suppose the temperature falls all of a sudden from 0 degrees centigrade, suppose it falls into negative side, say it has become say minus 5 degrees centigrade, okay? Now here temperature is minus 5 degrees centigrade, and here water comparatively it is at higher temperature, so water will start losing heat into the surrounding, okay, because heat always flows from high temperature to low temperature. So as the water from the top region loses the heat, it will be getting frozen. When its temperature is likely to be less than 0 degrees centigrade, it will be getting frozen, it will be transformed into ice. And don't you know, density of ice is smaller than density of water, so ice layer will float on this water, okay. Now below this ice layer, there is aquatic life which remains in water only. Here H2O exists in liquid state only because here temperature is more than 0. I am writing here 1 degree centigrade and the lowest temperature is 4 degrees centigrade, correct? Now tell me, why the water having temperature 4 degrees centigrade, why it is lying at the bottommost? Naturally, at 4 degrees centigrade temperature, tell me the volume of water is minimum, and when volume is minimum, density is maximum. So, among all these layers, because this layer having temperature 4 degrees centigrade has density maximum, then the layer with maximum density has to lie at the bottommost. So, here it will lie, correct? But in any case, all these layers have temperature greater than 0, and so all the aquatic life, marine life will exist here. They will not be getting destroyed, correct? And suppose if Almighty would not have attributed this property to this water, the property of anomalous expansion, then the way upper layer is getting frozen, all this layer also will be getting frozen, then all the aquatic life would have been destroyed. But right now they can exist safely, they are not destroyed because of which property? Because of this property called anomalous expansion of water, correct?